the question that a block of mass m is connected by the massless spring with the stiffness constant K to a rigid body wall moves without a friction on a horizontal surface. The block oscillates with a small amplitude A with an equilibrium position x0. Consider two cases. Means it says that this is supposed to be a wall, and here on this wall a spring is attached and it is connected with the mass m, and another mass small m is placed on this. There is small m and it is capital M. Okay, so when the block is at zero or a mean position, or when the block is at x0 plus a, that is amplitude, in the both the cases a particle of mass m, it is m, it's softly placed on the block, after which they stuck to each other as I shown the diagram here. Which of the following statements are true? The motion of masses m is placed on the mass m. Okay, so we have to find two things. So let's consider the case one. A solution here. Case one, applying conservation of. In the case one, we will apply conservation of linear momentum. Now, what is this? It is mv1 is equals to capital M plus small m v2, and let's say it is equation number one. So we will write it as v2 is equals to capital M upon small m plus capital M v1. Here, so this is our case one. Okay, I will also write it as, now we know that I can write as m a1 omega 1 is equals to m plus m a2 omega 2. Now we know that omega can be written as under root k by m. I will write it as under root k by m. So now here it is m multiplied by a1 under root k by m is equals to m plus m a2 under root k by m. So now what you will get? We will get the value of a2 here, that is under root m. Let me write it here, under root m upon m plus m, and that value will be equals to 81. Okay, so now we use the energy, which is kinetic energy, that is half m v1 square, and conservation of energy here. So E1 is equals to half mv1 square, and E2 is somewhat between energy of the second block is E1 half m plus m v2 square. Okay, so now we will write it as, or we will also write it as half m b1, or I can write it as half m plus m multiplied by m square v1 square. I'm just putting the values of the given value m plus m square. So now I will write it as half m, or small m here, n plus m square v1 square. So now look at this value here, e2 value, and that is equals to e2. So it is m square here. I will write it more clearly. It is half, this term is half m plus m multiplied by m square v1 square upon m plus m square. So this will be cancelled out and you will get the value of E2, that is half m upon m plus m square v1 square. Okay, so what is the value of here? Now you can see this term and this term. It will be clearly seen that E2 E2 is greater than E1. So the new time period T2 is equals to 2 under root m plus m divided by k here. And similarly, now if we will take the case 2, the new time period, the new time period is also here in the case 2. Let's talking about the case 2. New time period is come up to be T2, that is 2 under root m plus m divided by k. This is our new time period T2. So now you will see that with this time period, the amplitude is same in the both the cases. So A1 is equals to A2 in the new time period, and similarly E2 is equals to E1. That energies are equal. E2 is equals to E1. So the instantaneous value of speed at x0 of the combined masses decreases in the both the cases. So the instantaneous value of speed at x0 of the combined masses decreases in the both the cases. So the correct option is that amplitude of the oscillation in the first case changes by the factor of m. Yes, it is changes. You will see the equations here. This changes with the factor of m plus m upon m plus m. Then the second case, it remain unchanged. It remain unchanged as I show you. And the final time period of the oscillation in both the cases is same. No, it is not same. The D case is the final. The total energy decreases in the both the cases. Yes, the total energy is decreasing in the both the cases. So yeah, I hope you will get your answer and understand the concept clearly. Thank you.
Hello everyone, in this question we are given that there is a metal rod of length L and mass small m is prohibited at one end. A thin disk of mass capital M and radius capital R is attached at its center to the free end of the rod. Consider two ways in which the disk is attached. Case A, the disk is not free to rotate about its center, and case B, the disk is free to rotate about its center. So in first case, this disk can't rotate about this center, and in second case it can rotate. The rod disk system performs SHM in vertical plane after being released from the same displaced position. Which of the following statements are true? So we have to check these four statements are given, and we have to check these four statements. So first and second statements are about restoring torque, so we have to check the restoring torque and in case A and case B. So from here we are given that this is uh this is the rod, this is the disc, this is its out center, and this is let vertical axis, and it is making an angle theta. So the force on these are, this is capital mg and this is small mg, and this length L by 2 and this length is also L by 2. So from here we can see that there are only two forces that are responsible for providing power, capital mg and small mg. So if we write torque about any axis, let's take it about the vertical axis. So torque is force into distance. So this the mg and distance, this distance is L sine theta, capital L sine theta, and this distance is L by 2 sine theta. So in first case, if the disk is not rotating, case A, tau is equals to mg into L by 2 sine theta, here it is capital L, plus capital mg into L sine theta. And if the disk is rotating, so if the disk rotates, so it will not produce any force, so the torque will also be same in the second case also. So in case B, torque is equals to mg capital L by 2 sine theta plus capital mg L sine theta. So in both the case A and case B, the restoring torque is equal. So from here our first option is correct, and the third, fourth options are for angular frequency for case A and case B. So for angular frequency, if we consider in case A, the total energy of our system, that is total energy is PE, potential energy, plus kinetic energy, that is due to the translatory motion of the rod disk system about this axis. In this way it performs SHM. So about this translatory motion, it will be in case A. And in second case, case B, the total energy is equals to potential energy will be same, because there is no other force or the masses are constant and their position is constant, and the kinetic energy, that is also due to translation, and it is also through the rotation of the disk. So we can see there is no external force applied in both the cases. There are only two internal forces, that is capital mg and small mg. So in both the cases the total energy remains conserved, so no external force is applied, so energy is conserved. So if we apply energy conservation, that total energy at A and total energy in case B is equal. So in a first case, total energy is potential energy plus kinetic energy through translation of A is equals to kinetic energy through translation of B plus kinetic energy through rotation of B plus potential energy. So both the potential energies are equal, so these cancels out, and the translational energy is in case A is half m v center of mass of A square. Here total mass m is small m plus capital M, and in translational energy in case B, that is small m plus m into bc b in b case square plus half capital M, that is the rotation kinetic energy is due to only the disk, so disk half I of disk into omega square. So from here we can say that BCA will be equal this sum. So BCA will be equal that it can balance both BCB and omega. So BCA is greater than BCB. So the in a case the center of mass velocity is greater, so also omega in case A is also greater than omega in case B, because V is equals to omega R. So from here we can see that the angular frequency in case A is greater than angular frequency in case B. So our option third is correct, that angular frequency for case A is greater than angular frequency for case B. Thank you.
Hello everyone. Three simple harmonic motions in the same direction having same amplitude and the same period are superposed. If each differs in phase from the next by pi by 4, then which of the following is wrong? So the question is asking us to find out that which of these given three statements is wrong regarding the situation given to us in the question. To answer this question, we need to suppose the equations of three simple harmonic motions. Therefore, we suppose that these three are these equations given to us in the question. On superimposing these, we can write that the resulting SHM, which can be denoted by Y, will be equals to A multiplied by sine omega t minus pi by 4 plus sine omega t plus sine omega t plus pi by 4. Therefore, on calculating this, we find out that y is equals to a multiplied by twice of sine omega t into cos pi by 4 plus sine omega t, and therefore we can write that y is equals to a multiplied by 1 plus root 2 multiplied by sine omega t. Therefore, we can say that the resulting SHM, the resulting amplitude of the SHM, which was found out by superimposing these, is a 1 plus root 2. We also know that the energy of the resulting amplitude, which can be denoted by energy of resulting SHM, which can be denoted by E capital A, and energy of the initial SHM, which or the single SHM, which can be denoted by EA, their ratio is equals to capital A by small a squared. Therefore, substituting the values, we find out that EA divided by EA is equals to root 2 plus 1 raised to the power 2. And on further solving this, we find out that the energy of resulting SHM is equals to 3 plus 2 root 2 times of the single SHM. Therefore, on this calculation, we can clearly see that the statements statement 1 is correct and statement 2 and statement 3 are incorrect. Therefore, the correct answer is option C. Thank you.
According to question, two non-viscous, incompressible and immiscible liquids of density rho and 1.5 rho are poured into two limbs of circular tube of radius r and a small cross-sectional area kept in vertical plane as shown in the figure. Each liquid occupied one-fourth, okay, one-fourth of circumference. It means they makes 90 degree at center. So we have to find the value of theta that the radius of interference make with the vertical in equilibrium position. Okay, so according to question, these two fluids makes angle 90 at the center, means these two angles are 90. In that condition, if that angle is theta, that will be 90 minus theta, and that also 90 minus theta. Okay, so we have to find that value of theta. So we will balance the pressure at point A and point B, because we know that at same horizontal level pressure due to fluid remains same. So in that condition, pressure at point P1, pressure at point 1 will be equal to pressure at point 2. Okay, and that pressure is equal to rho gh, and density is given in the question. So first of all, we have to find the value of h1 and h2, means vertical height. Okay, so in the diagram, if that is radius r, so in that condition that height will be equal to r sine theta. Okay, similarly, if that is the radius and that height, okay, that will be equal to r cos theta. Okay, it means that h2 will be equal to r sine theta plus r cos theta, means r sine theta plus cos theta. That is the value of h2. Similarly, we will find the value of h1. Okay, so in the diagram, that total height, that is r cos theta, and in the diagram, if that angle is theta, so that height, okay, that is equal to r sin theta. It means that value of h1 is difference of r cos theta and r sin theta, means r cos theta minus r sin theta. So we will get r common, so cos theta minus sin theta. Now we will use that equation, p1 is equal to p2. So p1 is equal to 1.5 rho g h1 and p2 is equal to rho g h2. Value of h1 and h2 is 1.5 rho g r. h1 is r cos theta minus sin theta is equal to rho g r cos theta plus sin theta. Okay, so rho g r will be cut from both the side, so we will get and 1.5 can be written as 3 by 2, so we will get 3 cos theta minus 3 sin theta is equal to 2 cos theta plus 2 sin theta. It means cos theta will be equal to 5 sin theta, means tan theta, sin theta upon cos theta, tan theta will be equal to 1 by 5. So theta will be equal to tan inverse 1 by 5.
Question is given a point particle of mass m is attached to one end of mass less rigid non-conducting rod of length L. Another point particle of same mass is attached to other end of a rod. So two particles carry charge plus q and a negative q charge respectively. This arrangement is held in region of uniform electric field D such that rod make angle theta say about 5 degrees with the field direction. Means find expression for the minimum time needed for the rod to become parallel to the field after it is set free. So here in that position means this dipole here moment is minimum time needed when this is the rod become parallel means this will come here means the parallel to this rod. So how much time they will take? So now here firstly we have to find a dipole time period. So here we take this dipole. This is the dipole and here it's the here this is the electric field and this is the dipole. So this is the one and is the negative q charge magnitude of this dipole and here it's a positive q charge here. So now here dipole force on side electric means this is the direction of a force on this electric field direction here. So here electric field is uniform means keep any point charge. So here q charge means F is equal to q by E. Now here if this angle is theta, so here this is also theta and along this component is the QE cos theta and here this is the perpendicular of QE sin theta. And now here this is the tension T on this side. So here this dipole tension cancel out this force QE cos theta. So here we have to find when this time this dipole is come here this is equal to this. So now here we can write firstly rest forces will means this is the oscillation here SHM. So F is equal to Q is sin theta and now here sin theta we find this is the here we take this is the x and here this length is the L. So this half is L by 2 and here this angle is the theta angle theta. So here we find a sin theta is equal to x by L by 2. So here this is the 2x by L. So now here sin theta value put in this force. So F is equal to QE 2x upon L. Now here apply Newton law. So that means MA is equal to 2QE upon L and this x. So acceleration will come here 2QE upon MLF. Now here in SHM we see a relation in SHM. So A is proportional to minus X. So here that means when particle moves, so act a restoring force. Because of this, a negative sign will come here. This is a negative sign. Now here we find a omega. So omega square is equal to 2QE upon ml. And here omega is equal to 2QE upon ml means here A is equal to omega square x. So here we find omega. Now here we find that T is equal to 2 pi by omega. So here it is equal to 2 pi under root of ml upon 2QE. And now here we can time period its cover means here when it comes here. So here they will take a T by 4 and here it when this particle is come here. So here they will take a T by 2 and 3T by 2 and when it come here then they will take a T time. So means overall time periods cover only fourth part of the time period. So here we can write T minimum is this is the T minimum is they will take a fourth part means the fourth part cover of the time period. So here T by 4 is equal to now here we can write 2 pi by 4 into ml upon 2QE, and here this is the cancel out. So here it is equal to pi by 2 under root of ml by 2QE. So this is the time minimum needed when the rod becomes this parallel. So this is solution to this question, guys. Thank you.